Well, Phoenix is 1,000 to 2,000 feet, so Mount Everest is 29,000, I think.
Oh, okay, so it's more like 5 miles?
Right, so 5 miles, and each it's 3/4 inch to a mile, so maybe this is 3.5 inches. So it doesn't seem like a lot of difference if you're looking at a globe the size of a city block, but the planet is really pretty flat. The ocean is, in fact, the tallest mountain isn't Mount Everest, it's Hawaii, one of the islands of Hawaii. That's because the base starts below sea level and comes up above sea level. We'll be showing everything below sea level as a topological surface, or the terrain. Even the lakes, everything is showing the bottom of the lake, not the surface level. So
and what are the tolerances that you're designing for?
Well, that's why a laser is so important. We got a laser that gives us plus or minus 1/1000th of an inch accuracy for parts that are cut out. So it'll locate these positions of these standoffs or stands within 1/1000th of an inch, and it'll cut these dimensions between here and here to within 1/1000th of an inch. So that means that we can put all these really fine-tuned dimensions in, and when we have the tiles finally put on, even though they're all at a little different level, they'll all match up as close as we can get it from a manufacturing standpoint. So it gives us the ability to put a kit of parts together that we can send to a school, and in a week or 2 weeks, along with the help of some supervisors, we can have these schools become assembly sites that will put this whole thing together and have a very precise model of this part of the planet.
And what is it? What will the students learn by putting this together? What's your hope?
Well, when we've tried it in the past, the idea is to get a bunch of kids that haven't really done anything from a precision standpoint and introduce some sort of mentor that helps them, either a mechanic or an engineer or a scientist or some woodworker. I say, okay, we're going to build something that no one's ever even tried before, make a model of the planet this size, and we're going to do it with a precision that you haven't even thought about doing before. This isn't like woodworking where plus or minus 1/8 of an inch is good enough. We're plus or minus 1/3 of the thickness of a piece of paper in our precision. And then just the act of building it, kind of the barn raising, where everybody is able to contribute something, and then they study the part of the state or the planet that they're responsible for, and then mount it and know that they're part of this giant team that's doing something that is totally unique.
What makes the structures rigid right below the panels?
This is
right below the tiles. I mean, that you've got the
space frame here.
Not your space frame, but the what look like hexagons.
Oh well, these are basically little triangular pieces that all are connected together. They all have to move up and down because the panels that need more depth to them are closer to the ocean or farther away. They have to be different. So these are all laser cut. We call these spreaders because they stabilize and spread out the tiles. Otherwise, if they were just anchored at the bottom, they'd kind of flop all over the place. And in this way, we've got two surfaces that define the perpendicularity of these to this big spherical surface. Over the dimension of roughly 3 feet here, the Earth rises about 1/16 of an inch. Our model rises 1/16 of an inch. It's hard to see unless you sight along an edge.
And when you do all the tiles for the state of Arizona, what will be the total curvature from side to side of the state?
About 6 inches.
About 6 inches. So even though there's only 1/16 of an inch, by the time you add all of them up, you're going to have how many inches again?
6 inches.
6 inches
about
of curvature.
About 1/2 foot over the 30-foot diagonal of Arizona. So you'll definitely see it. It doesn't show up too much at this level, but it'll look as close to being in outer space as you can get. You know, this short of being an astronaut, you have the perspective that only people in space have.
So it seems to me like there's a fair amount of geometry that someone could learn from this.
Well, if you want to understand what's going on, it's all based on geometry. It's all based on just one of these tiles. We have the NASA supplies us the dimensions of one of these tiles, and from that one tile we can determine the geometry of where all the locations are, the overall sizes, put that into the computer, send it to the laser, and it cuts this out extremely precisely. So it's all based on knowing how things fit together.